Okay, so welcome to everybody, so welcome to this workshop. This workshop is okay. So welcome to everybody. Okay, I have to close YouTube, otherwise it. Okay, this workshop has been is organized by the team which participates to the project, the Marie Curie project, Big Math, which now has run for 3.5 years and is close to the end, let's say. We are happy now to host the students who participated to the workshop, that were enrolled in the workshop in the project, and we are happy to host the students and to let them present their research in the field of mathematics for big data. So I will shortly introduce. We decided also to include some speakers, keynote speakers, and that can give to our students some directions, and also to the audience, clearly, some directions on what we expect in the research of mathematics for big data, data science, artificial intelligence, which are clearly subjects which are very hot topics in this period, let's say. So I will start to introduce briefly, shortly, the project Big Math and how was it structured and developed during these years. No, I'm looking to the wrong, sorry, to the wrong, okay, file. So, no, again is the wrong file. In my case, at least, I have to close the other files, otherwise, okay, the other PowerPoints, otherwise I'm lost, okay. Okay, now I think that I'm sharing, hopefully, the correct file. The Big Math project has been funded from the European Union in 2018. It's running for 4 years. And is a European industrial doctorate, which means that is essentially a project for PhD training, in which companies, private companies and industries are quite involved, okay? So the project has a set of academic partners, which are University of Milano, the Technical University of Eindhoven, the Instituto Superior Técnico de Lisboa, so Lisbon, and University of Novi Sad. And then we have a set of 6 industrial partners, which are quite involved in the training of the students, in the sense that they essentially host also the students hosted the students for a long period to complete the training and to make them work with, let's say, practically on a set of industrial problems related clearly with data science, big data, and so on. So the overall aim of the project was and is to train a group of, in our case, 7 young students. You can see the picture of our students here, with a strong theoretical and practical skills which are needed nowadays to tackle the challenges of the big data era, which means, I mean, the particular techniques in mathematics, clearly, that are needed for facing the raising new problems, let's say. So the training and the research of Big Math were focused on, in particular, on problems of optimization, statistics, and large-scale linear algebra, which actually are some of the most relevant mathematical topics needed to produce good techniques of machine learning or artificial intelligence. And so essentially, they are the main ingredients which are needed then to build some data-driven methods in a good way. And the students, the projects of the students were developing 4 working packages, which were focused on 4 different mathematical fields of research in 3 different areas of applications. So this is a scheme of the working packages. Essentially, the 4 topics, mathematical topics that were faced were distributed optimization, stochastic geometric models, model reduction and features extractions, and statistical methods for imbalance classification. And these fields, let's say, research fields, were developed in particular related with 3 main areas of application, which was human face reconstruction, financial processes, and production systems. And clearly, we had also some working packages devoted to training and to dissemination of results and management, as usual. The projects, the industrial projects in which our students are working are essentially divided in these 3 main areas, which are also the 3 main parts of the workshop in which this workshop is divided, essentially. So the first one is human face reconstruction. And in this case, the students are collaborating with Trilateral, which is a company producing virtual reality for video games or movies and so on. And with Muroboptics, which is a company instead producing, for example, human prostheses, and so for the face, so for ears, nose, and so on. And so all the research that now our student will present also in their talk are related with essentially the reconstruction of realistic human faces or part of human faces, let's say. Then we had 2 projects in the framework of financial processes, for which we are collaborating with Chief, which is a company in Serbia, in Belgrade, SDG, which is a multinational company, consulting company, and Acumea, which is a company, a financial company in Milan. And the last area of application is to production processes. And in this case, our students again are collaborating with SDG, the consulting company. Essentially is based in Milano, the part of SDG with which we are collaborating. And with CU Lime, which is another consulting company based instead in Eindhoven. We clearly, being a PhD program, we had also to reach some training objectives, which were related with we wanted to in some way enhance the capacity of our students to have both careers in an academic framework if needed, but also in an industrial framework. So essentially, these kind of projects are really focused on trying to do a training which can be exploited in both environments and may come out with a true interaction and true collaboration between academia and company and industries. And so essentially we wanted to train, to give the students not only the theoretical skills needed to do the research, but also to give them the soft skills which are needed also to work outside the academia, let's say. And these objectives were reached through three main type of training. So essentially, we had a project-specific training, so a training of the students related with the specific industrial project that they were facing. And this was done clearly together with the companies and through some secondments to the companies for long periods of work in the company. Then we also offered some soft skills training, so some workshop and specific courses in which they were trained to develop some soft skills. I will show you a list of these courses later. And some joint research training, which means we offered essentially a set of advanced theoretical training courses offered by the professor, the academic partners of the project, and also some training courses related with, aimed to develop the modeling capacity, the mathematical modeling potential of the students. So the academic courses, let's say, that we offered were essentially in the four main working packages, fields of the main working packages, theoretical working packages of the project, and were offered fortunately in 2019 or beginning of 2020, so before the pandemic, and we were lucky that we could complete this training before the start of the pandemic. And then the student attended an ECME modeling week, the ECME student competition, and actually one of the teams winning the competition was exactly one of the team of our students. And also they participated to online competition and hackathons also launched by the European Commission related with the modeling of COVID-19 related things. And so these courses essentially, or competitions, were also aimed to train our students to act with real applications and let's say, in a framework which is in between research and academic research and working in a company, let's say. The soft skill training was done, clearly planned to be done during the secondments in the companies, but it was in some cases limited because of the restrictions of travel of COVID-19, and so some of the students did the secondments in person, and some of the students instead essentially worked from home in smart working for a long period. But we could effectively collaborate even using the smart working method, let's say, and the method of connecting and meeting regularly online only. Then it was offered the first course on soft skills in Lisbon, like entrepreneurship and how to write a CV and present a project and similar things. The students were invited in some cases to give a presentation at conferences. Many of them, unfortunately, were online, but anyway, they had to prepare some presentations to some also international conferences. We organized the regular reading seminars of our group, and so all the students were more or less one per month. One of the students had to present the advances of his or her work to the entire group of researchers of Big Math. And so in this way, they were trained to do presentations and also to stay, let's say, on to keep the group updated on the advancement of the research of each student. Then some courses, one on science communication and public engagement was offered in Milano, one on scientific data management that was offered by SDG, again, it was online, and the course on financial data management offered by SIF was also provided to the students. And some students were also involved in some local public events like the Night of Researchers, so of scientific dissemination, which are addressed to a general public. And unfortunately, because of the pandemic, these kind of events were mainly online. The supervision of the students was also organized in a shared way between academia and industry. And this means that essentially the meetings, the online, mainly online again, but the meetings, regular meetings with the students and the supervisors were including essentially always also the industrial partners. Okay, so it was not an independent supervision from academia, it was really a collaboration. And last but not the least, clearly I have also to thanks a lot the European Consortium for Mathematics in Industry, of which many of us in the academic framework are partners. Presently, I am the vice president and Natasha Kreitsch is the president, because essentially this project was possible only thanks to the collaboration that is present in ECMI. And the efforts that ECMI is doing to encourage groups of universities to collaborate in subjects of industrial mathematics. So really, we have to thank ECMI for their support and continuous support, let's say. Okay, thanks. I don't know if you have any question or comments. I think you cannot switch on the microphone, but you can write questions in the chat or raise your hand if you want, and then I can activate your microphone. So are there any questions or comments on our project? No, it seems not. I hope it was clear. So I think we can start with the, even if we have 5 minutes of, we are 5 minutes in advance, but I think we can start with the first keynote lecture, which is related with, so the first part of the workshop is related with the so-called challenges of geometry, which are essentially problems which arise whenever some, let's say, random geometry or random complexity which is related with geometry comes up and should be faced. So the first speaker for this part is Professor Patrizio Frosini from Università degli Studi di Bologna. Patrizio Frosini is a professor of geometry in Bologna and is one of the founders, let's say, or anyway, he posed the first ingredients to what now is called the topological data analysis, and now he's developing new methods which involve geometry to study new machine learning techniques that can be used for some let's say, more explainable methods, less black box methods than what we are facing up to now. So Patrizio, if you can, and the title of his talk is on the use of group equivariant non-expansive operators for topological data analysis and geometric deep learning. If you can share.
Good morning. Can you hear me?
Yes.
So I'm going to try to share my screen.
Okay.
Please tell me if I should be able to. Okay. Is that visible to you?
Yes.
Okay. So let me. Okay. So good morning. Thank you for inviting me to speak about group equivariant and expansive operators in this webinar. My purpose is the one of illustrating the basics of the topological theory of these operators. I will try to give a general idea of this theory. Maybe I will skip some details that anyway will be available in my slides. So this is the outline of my talk. First of all, I will speak about the main fact that data analysis is not just about data. It is also about observers of data. And then I will illustrate some topological and metric basics for the theory of GENIUS, group equivariant and expansive operators. Then I will recall some relevant results about compactness and convexity of the spaces of GENIUS. Finally, I will give some methods. I will illustrate some methods to build GENIUS. And finally, I will give 2 examples of use of GENIUS in applications. Okay, so first of all, we well know that data analysis is not just about data. Observers are quite important. Data interpretation strongly depends on the observer. If we change the observer, the analysis can completely change. This is trivial. We have this experience in real life. And so we have to recall that we are not directly interested in data. In general terms, we are interested in the reaction that suitable observers have in the presence of data. For example, if I have a skin lesion, I'm not interested in the image of a skin lesion. I'm interested in the opinion, the judgment that a physician has about this skin lesion. So we are interested in the reaction of observers, not in most of the cases, at least, not in data, but in reaction of data observers. Data analysis strongly depends on which of an observers. We well know that if data analysis were not dependent on the chosen observer, then physicians' diagnosis would always be identical. Scientists would always see the same causes for each phenomenon, and all people would agree in judging who the heroes and villains in a movie or a political event are. But this is not the case. We well know that. So we know that different agents can have different reactions in the presence of the same data. And so we have this idea. We have the basic idea that data analysis should study the pairs data observers instead of just the data. We have to start from the definition of measurements, since when we have an observer, we have actions made by this observer and measurements made by this observer. And if we have a look at Wikipedia, we can read that measurement is the assignment of a number to a characteristic of an object or event, which can be compared with other objects or events. And so measurements, in some sense, are functions. Functions taking each point in a set of characteristics to real numbers or vectors. But in this talk, I will limit myself to consider scalar-valued functions instead of general vector-valued functions. For example, we can consider these measurements, an electrocardiogram that is a special kind of function from the real number to the real number. Obviously, it is not true that any function from the real number to the real numbers can be seen as an electrocardiogram. For example, we should just consider bounded functions and almost periodic functions. But anyway, an electrocardiogram is a function. A gray level image is a function from the real plane to the real numbers. A computerized tomography scan is a function from a helix going around a human body to the real numbers. So these are examples of measurements. And I'm not saying that any kind of data is a function, but in many cases, we have that data are represented as functions that are produced by measurements. Okay, there is another information we have to take into account. Observers are often associated with invariance groups. For example, if we consider these two shells, we can say, in some sense, we can say that they share the same shape. And in this case, we can rotate and translate the object on the plane, the shell, and the shape does not change. So we could say that in this case, the group of isometries, or if you prefer, a larger group, is an invariance group for the concept of shape we are interested in, if we look at shells. But if we change our purpose and we consider letters, we have to change our group. For example, if we consider this letter M and this letter W, we recognize that we cannot apply rotation as an invariance group. These letters are different from each other. So when we choose an observer, we also choose an invariance group, at least in many cases. There is an interesting question here. what do the expressions data equivalence and data similarity mean in our setting? We say that two functions, phi1, phi2 from their domain X to the real numbers are equivalent with respect to a group G of permutations on the domain X if there is an element in the group, a transformation, such that phi1 is equal to phi2 composed G. For example, if I have two images of the same person and I put these images on the table, I can consider they equivalent if by translating and rotating one image, I can obtain the other. Obviously, this concept is not so interesting since we never have precise correspondence, but we are interested in similarity, and we have similarity. One, we have that the norm of phi1 minus phi2 composed a suitable transformation is small. And these observations lead us to define the basic concept in this approach to let me say, data and observer analysis. The concept of natural pseudo distance with respect to the group G. What is the natural pseudo distance? Let us assume that we have a topological space X and a subgroup G of a group of every possible homeomorphisms from X to X. We consider two data, the functions phi1 and phi2, and we consider the infimum varying the transformation in our group of a norm of phi1 minus phi2 composed transformation G. So we try to register one data with respect to the other. And the infimum of this cost expressed by the norm is the natural pseudo distance, obviously defined with respect to the group G. I recall that the pseudo distance is just a distance d without the assumption that when the value d of x1, x2 vanishes, this implies x1 equal to x2. We remove this assumption and we get the concept of pseudo distance. And why is this concept relevant in data analysis? It is relevant since we can look at this natural pseudo distance as a ground truth in data comparison, I mean topological data comparison, when data equivalence is expressed by the group G. It is interesting to observe what happens when we enlarge the group G. When the G is the trivial group identity containing just the identical transformation, we have the natural pseudo distance coincide with the max norm distance. When the group becomes larger and larger, we get obviously that the natural pseudo distance becomes smaller and smaller. And okay, so we have this basic tool to compare data in a topological setting. We usually restrict this natural pseudo distance to a subset phi of a set of continuous functions from X to R. I'm skipping detailed information about this concept, and I go to the next slide. Okay, so what are the basic assumptions in the approach I'm describing? We have these three assumptions. The first one says that the space of observers is often more important than the space of data. In some sense, we could say that no one is directly interested in data. We are interested in reactions to data. The study of a space of observers requires the development of a new topological geometric model able to study the topological properties of a space of observers. So not the topological properties of a space of data, but the topological and geometrical properties of a spaces of observers. And this new model could be of great use in data analysis when the role of observers is not negligible. These assumptions suggest us to move from the topic of topological data analysis to the new field of topological observer analysis. We know that observers are structures able to change data into other data, and usually do that by respecting some data equivalences, that is, by commuting with some transformations. As a first approximation, we can consider the concept of geo, which is a group equivalent operator. But we are mostly interested in another concept, the concept of group equivalent non-expansive operator, GENIO. I'm going to describe this in the next slides. Anyway, why non-expansive? Why we add this requirement? There are two reasons. First of all, observers are often assumed to simplify the metric structure of data in order to produce meaningful interpretations. And so we have to change the metric and to make it simpler in order to analyze data. I'm not saying that this always happens, but it is frequent in data analysis. And secondly, non-expansiveness guarantees good topological properties, and I will give one of these properties in the following. We have to consider, we start from functions. First of all, we have measurements, and we start from measurements. So we have a non-empty set X. Now X is not a topological space, it's just a set. And we have a set of functions, that can be produced by our measuring tools. And we call this set capital Phi. It is a topological subspace of a set of all bounded functions from X to R, endowed with a max norm metric. We can see X as the space where we can make our measurements, and Phi as the space of all possible measurements. We call this space the space of admissible functions. For example, as I told you, we cannot take any function from R to R as an electrocardiogram. We have to restrict the space of functions in order to have just the functions that can be seen as electrocardiograms. In our words, capital Phi is the set of all functions from X to R that can be produced by our measuring instruments or by our observers. For example, a gray level image can be represented as a function from the real plane to the interval 0, 1. In this case, the domain X is the real plane. Now I have to recall a technical fact. The initial topology is a topology defined on the domain X with respect to any function in our set is continuous. We define the initial topology in X as the coarsest topology in X, such that every function in capital Phi is continuous. By using this topology, we can always assume that any function in our set of possible admissible measurements is continuous. So I'm not saying continuous in the Euclidean sense, but with respect to this initial topology. There is another way of describing this initial topology when we have that Phi is totally bounded. If capital Phi is totally bounded, the initial topology coincides with the topology induced by this pseudo distance that says that the distance between two points, x1 and x2, is the supremum of the Euclidean distance between the values taken at these points by the functions, the admissible functions. So we are saying that 2D points are different if and only if we can find a measurement that is able to distinguish between these 2 points. And there is another technical fact, I just cite this. If the set of measurements is compact and X is complete, then X is compact too. And since we can always complete the set X, we can always assume that in case the set of measurements is compact, we can always assume that the set of points where our functions are defined is compact too. Okay, now some magic happens. If we use that topology, the topology that I have illustrated, each bijection is an isometry. If we consider, indeed, if we consider the group of all bijections from X to X, and we consider the subgroup of this set, the subgroup of the bijections that preserve capital phi in the sense that by composing any function with g and the inverse of g, we obtain another function in capital phi. If we restrict this set of bijections, we obtain this set of phi preserving bijection. And if we do the same for the homomorphism by obtaining the phi preserving homomorphism, and for isometries by obtaining the set of phi preserving isometries, we have this proposition. The set of phi preserving bijections coincide with a set of phi preserving homomorphisms, and this coincides with a set of phi preserving isometries. This is a consequence of a choice of a topology I have spoken about. And as we have done for the domain of a function, we can define a topology also on the group G we have chosen. The distance between two homomorphisms or isometries, if you prefer, in the set of the group G of our transformation, we can define the distance between two transformations G1 and G2 by using our set of measurements. We take the supremum varying the measurement of a max norm distance between phi composed G1 and phi composed G2. So we have that also G becomes a topological group, a topological space, and we can prove that G is a topological group and the action of the group on the set of measurements by right composition is continuous. So the setting is pretty good to go on. And also, we have a similar result as for the transformation in G. We have that if phi, the set of measurements, is compact and G is complete, then G is compact too. And since we can always complete G, we have that in summary, if the set of possible measurements is compact, the domain of the measurements and the group acting on the measurements are compact too. And compactness, you know, means that we can approximate with finite sets. And so this is quite advantageous for applications. Now we can define the concept of geo and geos. Let us consider two pair this definition. Each pair phi G with G a set of phi preserving a group of phi preserving homomorphisms. We have what we call a perception pair. So a perception pair is a set of possible measurements with an equivalence group that is associated to this set of measurements, and the role of this group is this group tells us what is the equivalence between data, between measurements. When two perception pairs are given, and we fix a group homomorphism between the two groups, the equivalence group G and H, we can have this equality. If this equality holds, the function f taking measurements in phi to measurements in psi is a group equivalent operator, a geo. And if we have also that this operator is non-expansive, so this inequality between the distances between data holds, then we say that f is a group equivalent to an expansive operator. Non-expansivity means that when we take the distance between the new data we get by applying the operator, the distance between the new data is less than the distance between the original data. This is just theory, so let me explain what I mean by giving you an example. Let us consider the Earth and the distribution of temperatures on the Earth. And we are interested in comparing these distributions, for example, at 2 different days, okay? Imagine that we have just the possibility of recognizing on the Earth the North Pole and the South Pole, N and S, okay? And now we can introduce two perception pairs, phi G and psi H, by setting X is the surface of the Earth, S2. Capital phi is a set of temperature distribution on the Earth. And we represent this distribution as one Lipschitz functions from from S2 to a fixed interval AB, where A is the minimum temperature that we can measure on the Earth, and B is the maximum temperature. G is the group of rotations of the Earth around the axis North Pole, South Pole. Then we have another perception pair where the domain of our measurements, Y, is the equator of the Earth. And psi is the set of one Lipschitz functions from the equator to the interval AB of temperatures. And H is the group of rotations of the equator. Now we can define a simple genome from the first perception pair to the second perception pair. We have to define the homomorphism between the groups, and this is quite easy. We associate to each rotation G of the Earth the corresponding rotation T of G of the equator. And as for the operator, we define for each distribution of temperature phi on the Earth, we define the distribution of temperature of the equator, f of phi, that is the function that takes each point y belonging to the equator of the Earth to the average of the temperatures along the meridian containing y for every distribution of temperature phi. And we can easily check that phi verifies the properties defining the constant of group equivariant on expansive operator with respect to the isomorphism, in this case the homomorphism. T is indeed an isomorphism. And in plain words, our genome transforms temperature distribution on the Earth into temperature distribution on the equator, but it is a smaller space. So we have a compression of information. This is the advantage of using genomes. Now I'm going to recall some property. We can define the suitable distance in the space of genomes between two given perception pairs. And we have a theorem that if the set of measurements phi and the set of measurements psi are compact, then the topological space of genome is compact too. So if we can, we have compactness for the data, we have also compactness for the space of observers. And so we can approximate with a finite set the set of observers. And furthermore, if the space of measurement psi is convex, then the space of genomes is convex too. And this is another advantage in computation. Now that we know what genomes are, we need methods to build genomes. And there are some simple methods to build genomes. For example, by composing genomes with respect to suitable groups, we get our genomes. Then when we have an image, one Lipschitz function, we can, and we have n genomes, f1, fn, we can use these one Lipschitz functions in n variables to build a new genome. One Lipschitz functions produce genomes from genomes. And as a consequence of this proposition, we have these three important factors, important for applications. Genomes are a lattice, have a structure of a lattice. Since when we consider the maximum of a family of genomes, we get a genome. When we consider the minimum of a family of genomes, we get a genome. Furthermore, if we translate a genome, we obtain a genome. And if we compute the convex combination of genomes, we get another genome. So we have some simple tools for producing new genomes. But I would like also to say something about not trivial ways of building genomes. And one maybe non-trivial way of producing genomes is based on permutant measures. So let us consider the set of all functions from a finite set X to the real numbers, and the subgroup G of a group of all bijections from X to X. We give this definition. A finite sign measure mu on the set of bijections is called a permutant measure with respect to the group if every subset H of the set of bijections is measurable and mu is invariant under the conjugacy action of G. This means that when you take the set of permutation H and you measure this set, you have that this measure coincides with the measure of this new set of permutation obtained by conjugacy. If we have a permutant measure, the important fact is that if you have a permutant measure with respect to G, then we have a map F mu associated with the permutant measure mu that takes any measurement phi to a new measurement obtained by this formula, and this operator is a geo, a group equivalent operator. So if we have a permutant measure, we have a way of building genius. Okay, let me give an example of permutant measure in order to make clear what I mean. Let us consider the set X of the vertices of a cube in R3. So it is just a set of 8 points. And the group G of orientation preserving isometries of R3 that take X to X. And now let us consider the 3 planes that you can see in the picture. The planes pi1, pi2, pi3. Planes that contain the center of mass of a cube and are parallel to a face of a cube. For each plane, we consider the orthogonal symmetry HI with respect to pi I. Now, we can define the permutant measure mu on the group of any permutation of the 8 points, the 8 vertices of a cube, by setting mu of H1 equal to mu of H2 equal to mu of H3 equal to a positive constant, and mu of H equal to 0 for any other bijections. Please consider that the cardinality of a support of this measure, in this case, is 3, and the cardinality of the group is 24. So the permutant is smaller, much smaller than the group. This is quite important since the computation with respect to permutant measures is quite simpler than the computation of the group G. And we have this representation theorem. This representation theorem states that when we have a group, a subgroup of a group of any possible permutation of X, if we have that this group transitively acts on the finite set X, and F is a map from the set of functions from X to R to the same set, we have that this map is a linear genio if and only if we can represent it by this formula involving our permutant measure. And the permutant measure has a total mass less than 1. So we have a representation theorem that says any geo of this kind can be represented by using a permutant measure. The last thing I would like to describe in my talk is the use of genius in applications. Let me give you a simple example, just a toy example in any sense, involving two classes of dice. You know that the dice we use in games have this property. The sum of two opposite phases is always 7. In this experiment made by Giovanni Bocchi, two classes were considered. One class is made of regular dice, where the sum of opposite phases is 7. And one class is a class of fake dice, where, as you can see here, two opposite, since you can see that 4 and 3 are adjacent, so the sum on opposite phase cannot be 7. Our purpose is the one of using genius in this toy example to see what happens to data. We produced 10,000 dice, a training set of size 7,000, and a test set of size 3,000. And then we applied the principal component analysis to the test set and to the test set transformed by a suitable genius, optimized on the training set. For each die, we consider the first two principal components. So for each die, that is represented by a function, a description of the colors on the faces of the die. For each die, we compress the information to just two numbers, an abscissa and an ordinate, that were plotted in these two pictures. On the left, we did this to original data, the original functions describing the dice. And blue points are associated with real dice, while orange ones are associated with fake dice. So you can see in this picture, this figure, that if we do not apply genius, blue points and orange points are mixed up. Okay, there is no clear distinction between the two classes. But if we apply a suitable genio, in this case, the genio was built by convex combination of three genios defined by permutant measures. If we apply genios, you can see that the data are pretty clearly separated. And genios do that, change data in a way that make them more easy to use, more easy to use. Okay, now I would like to move on to describe a real application that is described in this preprint, GenioNet, a new machine learning paradigm based on group equivalent and expansive operators, an application to protein pocket detection. What is the problem that we face in this preprint? We consider proteins. And for example, in this picture, you can see protein 2QWE. And we are interested in locating pockets, these cavities where you can have, where the protein can host some ligand, so some drug that can interact with the protein. And so it's important in application to localize these cavities, okay? And there is a lot of research as for this topic, and you can see on the right the detail of some cavity. In particular, you can see in one of these cavity, the ligand, there is a small drawing in red, that is the ligand that is hosted in this cavity. And you can see more cavities since obviously there are many locations where there is a possibility of docking. So we have to compute these to localize these cavities. The search for the pockets in our experiment was carried out by identifying an optimal genome in the convex hull of 8 genios, each focused on a particular property of the pocket. So we have a family of genios, each one is thought as an observer looking for some property of the pocket, and they cooperate, and this cooperation is given by convex combination. And now this is what happens. Here are the results of our experiment. This line is the line of results given by GenioNet, which is a shallow net based on genios. This net uses 17 parameters, and you can see our methods in this plot. In particular, I underline that deep pocket, it is another method in green, requires more than 500,000 parameters instead of 70. So this is the advantage of using genius. We have a method based on a transparent evaluation of what we need in order to solve a problem. In case we have some knowledge about the problem, we can try to make genius suitable for solving the problem. And the number of parameters is usually much smaller. In perspective, the main point in our approach is that in perspective, we are looking for a good compositional theory for building efficient and transparent network of genius. Some preliminary experiments suggest that replacing neurons with genes could make deep learning more transparent and interpretable and speed up the learning process. This is the main idea, replacing neurons with genes. And there are obviously many open questions. I read some of them. How can we approximate the real observer? Let us say, for example, a physician by genes in order to emulate her behavior with respect to data. Can we devise constructive procedures allowing us to build any possible genome with respect to a given equivalence group? What is the right way of comparing genomes in a topological statistical setting? How should we select representative sets in a probability space of genomes? How can we compute the basic statistics for genomes? How can we predict the behavior of networks of genomes and control their actions? How can we evaluate the advantages and limits of an approach to data analysis based on the interaction of genomes and TDA? Some references as for the topology and geometry supporting this approach, there is this paper towards a topological geometrical theory of group equivalent non-expansive operators for data analysis and machine learning. Then, as for the theory of permutant, you can have a look if you are interested in that. At this paper on the construction of group equivalent or expansive operators via permutants and symmetric functions. And then there is the preprint I have spoken about, GenioNet, a new machine learning paradigm based on group equivalent or expansive operators that is available on the archive. So, I'm done. Thanks for your attention.
Thanks, Patrizio, for your nice presentation. So, are there any questions? Maybe you can write in the chat if you have a question, or you can raise your hand. Maybe in the meanwhile, I have a question, in particular with respect to the distances that you mentioned, because you mentioned a lot of distances that are used essentially in this framework, but which of them are really computable in practical applications, in particular to compare different results of the genes, I mean, different processes of the processed data, let's say, no?
This theory is thought as a tool in topological data analysis. As you know, in topological data analysis, one of the main tools that is used is topological persistence. And persistent homology and persistence diagram are tricks to get a fast comparison between data. So the distances I have spoken about should think as distances that can be approximated by means of tools in persistent homology. So the direct computation should not about these distances, but about persistence diagrams. And we know that the computation of persistence diagram is, I shouldn't say pretty fast, but anyway, is practical. We can compute persistent diagrams. So the distances I have spoken about are a theoretical reference, but in practice, we are thinking of considering it in the future, not a comparison via those distances that are not so practical for computation. Instead of using them, we are planning to use shortcuts in persistent homology. So lower bounds in persistent homology.
Okay. Thanks. We are still looking to your screen, just to inform.
Sorry. I should be able to stop the sharing, but
Should be on the top.
Actually, I'm not able to do that. I cannot see. I cannot see the button for maybe.
On the top usually is on the top of the screen. There is a button.
Okay, I see new. No, I just see new sharing. Am I sharing my? Okay, okay.
Yes, we are. Okay, now yes.
Thank
you. So, any other questions or comment from the audience? No, it seems not. So, thanks again for your nice talk. And I think we can pass to the next speaker. Thanks again to I will clap for everybody because okay. So the next speaker is Filippa Valdeira from University of Milano. So Filippa is a PhD student in Milano, and she's working with the company Muroboptics in Lisbon. And she will speak about Gaussian processes for shape modeling and registration.
Okay, thank you so much for the introduction, and good morning to everyone. I will start sharing my screen now. Okay, is it okay?
Yes, yes.
Okay, so the title of my talk is that Gaussian processes for shape modeling and registration. First, I will.
Sorry? The screen is not full screen. Is
oh, it's not?
No.
In my computer? Well,
maybe it's better if you.
It's still not?
No.
Okay, maybe I'll try to share it again.
Okay. No, we are still looking to the. Okay, now yes.
Now it should be okay. Yeah. Yes. Okay. Thank you. Okay, so first, this is an overview of the talk. I'll start by introducing the problem and some basic concept that we will need later on. Then I will introduce the framework of Gaussian processes to perform shape registration and fitting. I will provide a small background on Gaussian processes, and then I will explain how the whole process takes place. Finally, I will move to the main content of the talk, which is the new registration algorithm within this framework that is inspired in probabilistic registration. And I will finish with some representative results, and then conclude with some final remarks. Okay, so first, when we talk about shape modeling, shape analysis, we are usually focusing on two shapes. We consider a template shape, which should be a representative example of the shape that we are considering. This is a good, let's say, good shape with no problems, and it should be, let's say, you can picture a mean shape, a mean example of this case. And then we have some random sample that we take, and we assume that this shape can be obtained from the template through some transformation model. However, we also need to take into account that these are unordered point sets. And so we need to, in specific, we need to consider some permutation of the points that allows us to consider a correspondence between points with the same semantic meaning. And so usually we want to solve the problem of fitting the shape fitting the template to the shape in order to minimize some chosen distance. We select some parameters that control our model, and so we want to find the parameters that minimize this distance. Okay, furthermore, we usually have the presence of both outliers and missing data in our samples. So outliers would be points that are in the shape but not in the target, or not in the template. And missing data is the inverse. So this is related to points that are in the template but then not in the shape. This, of course, adds some complexity to the problem. Okay, so now we want to position the Gaussian process framework in the literature. And the fact is that when we consider this transformation model, we can take into account only similarity transformations, but also non-rigid deformations. And this is the case that we are interested in, because for more complex examples and realistic, usually we are taking into account that the template can suffer non-rigid deformations. Usually this problem is approached in two different ways and in two different areas of the literature in different aspects. So when we consider that the non-rigid deformations are constrained by some generic notion, so for instance, we can say that nearby points should deform in the same way. This is not specific to the shape that we are considering. And so this is usually approached in the registration literature. So here we focus essentially on the correspondence part. We take a generic transformation model and we want to find the best correspondence between the template and the shape. Then we have the same problem, but usually called as shape fitting in the area of statistical shape models. And here we are constraining the deformations based on data. Of course, this is assuming that we are having prior data for this particular shape. So this is not a generic model, but this is based on the particular shape that we are considering. But the fact is that this is the same problem. And so in Gaussian processes framework, we take this problem into the same aspect, let's say. So in most shape analysis pipelines, what happens is that first we take a registration method because we want to enjoy those nice properties, and we establish a correspondence. And then when we have all the shapes in correspondence, we build a statistical shape model. And the most standard way would be to use a principal component analysis. And at the end, we will have a statistical shape model. The idea here is to always use the same model, both for registration and for shape fitting. And this is the purpose of this framework. Okay, so in particular, here we are dealing with head scans, 3D head scans, and in particular with the ear region. So we can see here an example. In this case, we would have a reference shape like this and a target shape like this one here on the right. And we can see immediately that this data is subject to high prevalence of missing data. And this is a problem that very much impacts the correspondence part and consequently the model that we can obtain. It is also subject to noise and some outliers, but the missing region is the largest problem that we face. Okay, so now a small introduction on Gaussian processes. A Gaussian process is a collection of random variables, and any finite number of which have a joint Gaussian distribution. Okay, so a Gaussian process is characterized by a mean function and a covariance function or kernel. And now we will see a bit better what this means. So when we define a mean function and a covariance, we are essentially defining a set of functions that we can allow. So the mean and the covariance are here defining the prior of our functions. Then in this work, we are interested in Gaussian process regression. And if we are given some data sets of points and observations, we can use them to produce our posterior, which is also a Gaussian process. And then we can predict unobserved data from this posterior. So the predictive equations for this case are here stated. And it is important to notice that we also required an observation noise. And this tells us how confident we are in the observations that we have, so in our data. Okay, so now how can we formulate the shape problem in this context of the Gaussian process? So we have a template and a target, which are point sets in some dimension d. And then we consider that we can obtain the points in our target as the template points plus some deformation u. And this deformation will follow a Gaussian process with a given mean and a given kernel. And one of the reasons that makes this Gaussian process very suitable for shape modeling is that the kernel provides us with a very intuitive way of expressing shape properties. So if we want to enforce the same deformation that I spoke about before, that nearby points should deform in similar ways, we can use an exponential kernel, but we can also use different deformation lengths for different scales. We can also enforce symmetry and much other properties that we know about our shape previously. A detail is that Gaussian processes are usually formulated for single output case. So we have an input that can be of any dimension, but the output is usually a scalar. When we want to apply this to the shape problem, we need to consider a multiple output. Fortunately, we know that we can obtain from any kernel that we already have defined for the scalar case, we can obtain a valid covariance function by multiplying with any symmetric positive definite matrix. And so the value, all the results that we have for the scalar case remain valid for this matrix valued case. And this, of course, is very helpful for us because in particularly we can use the identity matrix if we don't want to enforce any relationship between different dimensions. Okay, finally, we just need to define the vector formulation for our shapes that will sometimes be required, which is just a concatenation of the several points of the shapes. And also we will define the Kronecker product with the identity matrix as the initial vector or matrix with tilde. Okay, finally, for the outliers in missing data, we consider that we can split our templates and our shape into two subsets. So when we have some correspondence given between S and T, then we can split S into points with correspondence and missing points, and S with the corresponding part and the outliers. And so when we consider the set of deformations observed between these two shapes, we only consider the deformations between points in correspondence. Okay, so now how do we formulate this problem taking into account all these notions? So conceptually, this is usually formulated as a maximum a posteriori problem. And so we want to obtain the deformations U that solve this problem given a certain template and a target. In specific, we only care about the points with correspondence. So Tcoq and delta. But the fact is that this correspondence is also dependent on the deformations, because given a certain deformed template, we will have a different correspondence that is most likely for that setting. And so the problem is usually split into an outer and inner optimization, where we set U fixed for the inner and we set the correspondences fixed for the outer. So the usual way to turn this conceptual problem into a practical one is that we take the inner part as a standard correspondence, and so we can use a generic registration method. The most simple one is to take the closest point with respect to the Euclidean distance between both shapes. And so given that correspondence, we can then solve the outer problem. And so in this case, since we have a set of observations, so the point, a set of points, so the template points with correspondence and observations, the deformations, we can use the Gaussian process regression equations. And since we are in this setting, we know that the solution for the maximum a posteriori problem can be given by the mean because this is equivalent to the mode of the posterior. Okay, so now visual representation of our problem. We have the template shape. We detect correspondences. So we say that the points in green are in correspondence with the template. We get the deformations here represented by these arrows. And then we will do the step of Gaussian process regression, giving us the prediction for the missing parts. So this is done iteratively until we achieve convergence. Okay, in our previous work, using this framework, we concluded by comparing it with other approaches that this is in fact very promising for this kind of data, especially because we have so much missing data. And so we have established a pipeline that involves first removing the largest components, so rotation and translation, and then using Gaussian processes to do shape fitting and registration. This first part is important because we are assuming that the deformation should only represent small portions of rotation and translation and mostly non-rigid deformations. But still, we can see that this approach has some limitations. So for instance, because we are using the closest point, sometimes our template will collapse on the sides, or we cannot reach the full shape, or we get bad results like this one in general. And so this is the main motivation for our approach in the next section, because the way to improve this method would be either to focus on the correspondence part or to work on building a more accurate model. Here we will focus on this first part, and the way we will approach this is to replace the correspondence by a probabilistic assignment. And so what does this mean? In the first part, what we were doing was this correspondence where we set a point of the target to correspond to a point of the template. But now what we want to do is to, for each point of the template, attribute a possible correspondence to a target point with some level of confidence that should be set. So if we have some number of targets, we will have that same number of possible correspondences. And the way that we chose to express this within the GP framework is to use multi-annotators. So what does this mean in this context? We can understand the different deformations for each point as different labels given by different annotators, which in this case would be the target points. And so in the case of the multi-annotators, we will get predictive equations for the regression with a very similar structure to the ones that we saw before, except we have a different covariance matrix that now takes into account all the variances that we set before. And for the observations, we also should take into account all the annotations. Okay, so the question remains of how to compute these variants. So how should we express this confidence? Because an intuitive way is that it should be related somehow to the distance of point of the template to the target, because of course, if our deformed template point is very close to a target one, then it's highly likely that they are together. And so the variance should be inversely proportional to this. But to do this in a more principled way, so to have an actually update for this variance value, we can establish a parallel with standard probabilistic registration methods. And this is the part that we'll be focusing on now. So first we will state our model in this context of probabilistic registration, which has a bit of a different notation and ideas behind. But at the end, we will be able to establish a parallel between both and obtain a good update for our variance values. Okay, so the transformation model we consider is the same as we had before. We had our points plus some deformation. And now the model behind this is the Gaussian mixture model. So the template points are considered to be centroids that will generate the different target points. And so the distribution of the jth target point will follow a multivariate normal distribution that is expressed here, where we note that we have different variances for each point of the template. Okay, then the joint distribution of point Sj, taking into consideration all of the template points, will be given by this expression. So we have here some new variables. Essentially, this we should look at this first term as the probability of it being an outlier. So Cj is an indicator variable that tells us if the target point is an outlier or not. And if it is an outlier, then it should be generated from this probability, which is usually taken as 1 over the number of points in the target. And then we take into account all the points in the template to generate the target point. This 1 over nt represents the membership probability, so the probability that a target point belongs to some template, and here we consider that it is the same for any point. And finally, we consider prior on the deformations, which we can see that it is equivalent to our Gaussian process assumption on the deformations. So we have here the kernel as we had before. And so with all of these, we can get the full joint distribution that depends on these parameters, the deformations, the variances, and then the, well, sorry, this is an N, but it should be actually an E, that express the probabilities of correspondence. So a way to solve this is by using variational Bayesian inference, where we will approximate the posterior by a distribution Q, which we will assume that can be expressed by these independent Qs, each one depending on a different parameter. So the aim here is to minimize the Kullback-Leibler divergence between the posterior and Q, and we know that the optimal Q will be given by this expression that essentially depends on the expectation of the joint probability with respect to the remaining Qs, so all of them except Qy. Okay, I'm going over this quite briefly because this is not the main point. So finally, we can achieve an update equation for each of our variables. So first we look at the deformations update, where we are updating the expected value and the covariance. Then we have the correspondences update, where we note here that we introduce a new variable Pij. This represents the probability of correspondence between point I in the template and point j in the target. We also define this new that essentially will tell us how many points have correspondence with a given point in our templates, and the matrix P, which involves all the Pij. Okay, finally, for each term in the variance, we will have an update equation with this format. So with all of these, we can establish a parallel between our initial equation of the multi-annotators regression and the equations that we saw previously. So if we set the variance for our labels like this, we will get the updates for the variance and deformations in the multi-annotator case with this shape, and replacing them. I'm sorry, I forgot to say that this assumes that we are considering no missing points. So this is for the extreme case that we have 0 missing points. And so we would have an update equation like this for the mean deformation. And so we can formulate our update equation in this way by replacing these expressions into the initial one. And finally, the update for the probabilistic regression that we saw in the previous slide can also be formulated in the same way. So now if we are taking the update for the variance as the one we saw in the previous slide, and taking Pij also with the same expression, then we have a complete parallel between these two approaches. So we will take this as a reasonable value for our variance. Of course, we will not have the parallel anymore when we go to the case of missing points, but we still assume that this is a reasonable value for the variance. So finally, how we are establishing the missing points, we are taking some threshold on the probability values, and then we are defining the set of corresponding points as the points where we have no correspondence above that threshold for the given template point. Okay, so now some representative examples. We have here these data, these are fishes, and we have the target in blue and the template in red. This data set was generated with small rotation, translation, and scaling, non-rigid deformations, some noise, and variable levels of missing data. And so here we first illustrate why our method would be necessary instead of just using a random probabilistic one. And the fact is that in a probabilistic method, we should define how much non-rigid deformations we are expecting. And this is a parameter of the method. So the problem is that if we set this to allow a low level of non-rigid deformations, then we cannot accurately fit the shape because it is too rigid. However, if we allow for a high level of non-rigid deformations, we will face situations like this because we have no points in this area due to the missing data. And so the shape will try to correspond with the existing ones. With our approach and the threshold for the missing data, we are able to set a sufficiently low level on the non-rigid deformations. And so we are able to correctly fit this part while still maintaining these and identifying the missing points. Okay, so finally we have the results for a full data set. Here on the left, we have the distance error of the deformed template, then we have the recall for the missing points and the precision for the missing points. On the x-axis, we can see an increasing level of missing data. So the region from which we take the points is increasing from 1 to 5, where 1 we have no missing data. And so in red, we have the GP approach with the closest points, which always have the worst results except for the precision for high missing data. And then we have 3 different settings of our method that explain why the different parts are necessary. So in blue, it is the full method that we can see that for higher levels of missing data has the lowest error, and most importantly, it has a very high recall. And so this allows us to correctly identify the missing regions, which is very important in our case for the year's data. And then we have 2 variations, which is where one we use the variance usually taken for the probabilistic method, and in the second we use no threshold. And we see that we need both of these conditions to have the lower error and the high recall. And so finally, we have seen that this framework is very benefiting from the probabilistic correspondence, and we can formulate this idea with multi-annotators. And finally, we can establish a parallel between these 2 frameworks that allowed us to compute the confidence in each of our labels. And from the results, we see that this is very suitable for the cases with high prevalence of missing data, such as the years. So the next steps now would be to develop the kernels, because if we can accurately identify the missing regions, then we are very dependent on the prior, so on the information given by our kernels to fit these missing regions. And secondly, we should understand better in theory how this parallel would extend when we drop the assumption of having no missing data. So that's it. Thank you for the attention.
Thank you, Filippa, for your presentation. So, are there any questions or comments? Well, maybe can you comment a little bit also on the computational costs of this method that we implemented? So how big are the computational costs, let's say?
Yes, well, the cost of working with Gaussian processes for large data are, of course, very high. So when we move, well, in the year case, it's still reasonable, but if we would like to move for the entire head, it would be definitely a limitation. But the fact is that within the Gaussian process literature, there are a lot of methods to deal with this computational complexity. And so also a possible direction would be to work on this part to ensure that we obtain a method that is highly scalable.
Okay, thank you. So other comments or questions? No, maybe not. So we thank again Filippa for the nice presentation. And even if we are still a little bit earlier than planned, but we can go with the next speaker, which is Rongjiao Ji, that is still a student at the University of Milano, is PhD student again in Milano, and she's working with the company Trilateral in Novi Sad in Serbia. And the title of her talk is Group Pattern Detection of Longitudinal Data Using a Functional Statistics Framework. Again, we see also the next slide.
Sorry.
I don't know why, but today.
So probably I also quit it.
Yes, it's better if you quit the sharing and. Now it's okay. Okay. Try. Okay. Yes, it's moving, so we are done.
Yeah. Okay.
Thank you.
Yeah. So good morning, everyone. I will start my presentation with this title: Group Pattern Detection of Longitudinal Data Using a Functional Statistics Framework. So I'm Rongjiao Ji from the University of Milan. And this work is a cooperation between the University of Milan, the University of Novi Sad, and also the industrial partner, Trilateral. And I will start my presentation for briefly talking about this motivation of this work, and then the data related with the data we want to work with, and then the simulated data, and then the methods together with the results and with some conclusions. So for the motivation, we know that in research, normally in science, researchers, sorry, researchers normally separate the common emotions into 8 classes, including neutral, calm, happy, sad, for example, to the surprised. And the data set we are considering here is so-called the RevDice data set. It is open sourced and has high quality videos inside. So these videos are performed by 24 professional actors, and they are based on 2 common statements. So it's easy for us to study across the emotions and across the actors. And there are important concept of action units we need to know before the continue study. Sorry, very good to see here. Yeah. Sorry. So in computer graphics, normally they have this FACS, so-called the facial action coding systems. So it's a common and standard system to automatically categorize the facial muscles movement and then to transform it into the temporal profiles. So this temporal profiles is the action units we were studying on. So for example, if you look at the pictures here, one action unit relates to the contraction or the relaxation of one or several facial muscles. So in this way, we can transform the face movements in the videos into this action unit evolution curves. So there are basically three objectives we want to work on during this study. So first, we want to extract out the action units, for example, from the videos, and then we need to register them into the common timeline. And then we need to explore the latent patterns of these facial expressions so that we can find the common patterns just related to the emotions regardless of the performers. So finally, we want to use the registered curves and then the latent patterns to make some classifications to identify the expressed emotions or the mixture of them. So let's look at our data. So you can see, like in this left side, it's video from Revdice. So this actor is performing under the emotion disgust. As I said, we can use some kind of software, for example, this OpenFace, to generate a set of action unit series. So for example, here I showed you some action units related with the eyebrow, the nose, and the lips. So you can see how they evaluate along this timeline. And then also, alternatively, if we predefine a set of action unit series, and then we can give it to the computer through some softwares like Maya. So we can give this as the parameters back to the 3D facial models and then generate the facial videos. So that's kind of the reason we use the intermediate data of this action unit as our study objects. So one thing we need to do after extract out the action unit curves from the videos is that we really need to take care of the curve registration part. You can see here like two simple examples. These two actors are performing even though under the same statement, under the same emotions, but they are performing with the different spoken speeds. So like if the observed timelines is not registered, and then we can really sometimes lose the information of the shapes, for example. So we performed like this curve registrations on the action unit 12 related with the lips. So it's mostly influenced by the pronunciation of the sentence itself. And then we can see after the registration, we were able to study vertically across these emotions, across the performance of the actors, to study the shapes and where it starts to appear for the peaks. So we will talk about the strategy behind later, but this is like the registered curves that we use as our input data later. So actually, like for that Revdice data set, it has good qualities, but we actually don't know what is the ground truth of the latent pattern we want to find. So we consider this simulation process by giving them similar settings for the simulation data to the rev-dice data. So we fix the groups, the number of groups to be 8. So these groups to mimic the emotion groups. And then we set 3 independent simulated variables to mimic this action unit. So following the same setting, we first assume like they have this common mean curve in green. So you can see it's the same across the groups. And then for each specific group, we set a different kernel curves. So in color red, you can see. So this, we try to mimic the additional group effects. So not related with the mean, not related with the pronunciation of the sentence, like that. And then under each pair of this group variable subset, so under each window, we generated like 24 samples by adding randomly the Gaussian noises. And also we can add the noises with different standard deviations so that we can better test our model, like how efficient it is with different cases. So to summarize, this is a framework of the simulation process. So first we generate the simulated data with a common mean and then the several kernels for each variable and add some noise to make the samples. And then we use this FANOVA model that I will introduce, I will talk about more later. So with this model, we can transform the time series into this functional data. And then we want to estimate the parameter functions so that it can tell us back the additional groups and then the common means. So next we perform this statistical tests, including some classical or permutation tests. This is in order to detect the significant time zones. And then we go back to check the model performance by comparing the results and check the efficiency on different noise levels. So for our methods, I will mainly talk about these 3 parts. Start from the introduction of FDA as a basis of our study, and then we move to the model of the linear regression and then the test part. So for the functional data, so normally, like for in reality or for our researches, so we observe this discrete high frequency trajectory points. So for example, like this blue point here, it's discrete and actually under the idea of functional data analysis, given a set of functional bases, so for example, here I show you the B-spline basis, we can construct a linear combination of this functional basis together with coefficient matrix. So we can see that in this way, we can change this discrete time points into a continuous curve by adding the different coefficients for the different bases. So this is the basic idea that we transform the time correlated points into one smooth curve so that we can analyze the entire evolution process and capture the main shape characteristics. So again, like as we said, we need to do the curve registrations. So under the setting of functional data, it is actually more efficient to do the registration by separating the amplitude variability from the phase variability. So this amplitude variability is the information actually we want to study. And then the phase variability is the variance caused by the unregistered timelines from different samples. So we want to exclude them. So the training process is similar to the EM algorithms. So basically, at the end, we want to get the optimal estimation of these time warping functions so that for each observed timeline of each sample, we can find the way to connect it back to the internal registered timelines so that we can transform the data into a more concentrated way, as I showed you in the data visualization part. So for the second part I want to tell is the linear regression that we built. After the register of these curves, so we have this y dkg to denote the function object that we obtained for the variable d in sample k and group G. So we assume that we can build this linear regressions so that we think the curve can be the combination of the ground mean function denoted by mu d0. So this is the mean itself independent from the group information. And then this alpha dg. So here installed all the group additional effects related with the variable d. And we actually have this constraints to be satisfied while doing the calculation. And then this epsilon contains the unexplained individual noise. So by we can actually write them into this matrix form with very elegant format by collecting the samples from the same groups together, laying them in this vector, and then we just need to build this design matrix so that the mu of this mean and then the additional group effects, the alpha, or the parameter functions we want to estimate is installed here. And then this is arrows. Yeah, for if we combine all the variables, and then we can get the matrix format with all the samples together across the variables, across the emotions containing the constraints. So as we said, like in the functional data setting, we can rebuild the observed curves by considering the combination of the functional basis and the related coefficient matrix. So this Y can be rebuilt as matrix A with the family basis theta t, and then this parameter matrix can also be rebuilt as B with parameter basis. So actually here B is the same as parameters. B contains the parameters we want to estimate. So the process of estimating it looks like a mess, but actually the idea is very easy if we just do the least square estimation on the functional basis. So it involved some calculation of the tensors, but finally we will reach the value of B, and then instead we can transform it through the functional basis back to reach this beta. And so now we were already able to estimate our common mean functions and then the additional group effects. The goal of the test here is to investigate when and whether the group labels are significantly influencing the changing of the variables. So for example, like if a person shows the emotion happy, and then what would be the main characters you can see from her face, like if she's moving like the cheek at some time point, or she is keep doing like opening the mouth or something related. So we can perform first by the classical test. So first, for this classical test, still considering our big model containing all the samples. And then let me first bring you the concept of the contrast. So contrast is actually a combination of variables with coefficients summing up to 0. So the use is here to test pairwise contrasts between groups. So as you see, like we can fix the correlated indexes of these parameter functions so that we can do the assumptions following the following this way. So probably here I show you an example you can understand better. Here we need to assume that the observed curve is following Gaussian distribution with the mean mu I and sigma square. So the index I here denotes the every pair of variable and groups. So imagine that we have 17 action units and then 8 emotions. The whole pair of variable emotion group will be 70 multiplied with 8. So we can get the group sample mean in this way. And then if we contract the contrast in this way as a combination of the index vector together with the parameters we want to estimate. And then we can see that this one is actually an unbiased estimator of the construct by checking the expectations and then the variation of the contrast C. So here, for example, if I specifically define the index of action of a variable D and group 0 to be 1, and variable D group G tilde to be -1. So my purpose is actually testing like, is there any difference between the additional group effects of group 0 and group G tilde? So for example, like our goal would be to test considering on the cheek riser, the action unit 6. And then is there any difference when people show happy or when people just pronounce the sentence in a neutral way? So it will go to this F statistics under null hypothesis, so that we can compare the statistics we obtained with the critical values of F with the level that we set. So I'll show you some results later on. You can see like the region that was detected by this test method. Another method for the pointwise ANOVA test is to use the permutation, because here we already mentioned that we need to assume the curve to have some normality distribution. Well, for the permutation test, we can lose that constraint. So we can use the permutation to estimate the F test by shuffling the sample set. So, for example, in this way, we need to consider a smaller model only contains the observations within two groups. So, for example, if we want to compare again the happiness with the neutral on the cheek riser variable, and then we need to collect all these samples together and then rebuild this design matrix. So the estimate, so the parameters we want to estimate in here is just the additional neutral effect and then the additional happiness effect. So in this way, our hypothesis will become like, given the additional effects to be the mean of the samples, and then is there any extra happiness effect? Like, is the happiness effect 0? So similar to the previous one, for the linear regression with the ANOVA, we set this F statistics by considering the variance between groups and then the variance within the groups. So we can estimate the distribution of this statistic, F statistics, by shuffling the sample size. So here we shuffling the labels of these curves and then estimate all the possible values of the F distribution. So at the end, we need to compare the observed F statistics with the critical value at, for example, 90 quantile of this permutated F distributions to decide where we should reject the null hypothesis. Yeah, so till this moment, we already get the common mean curves and then the additional group effects. So how we can use them? Given a new curve, we can first do the centralizing to remove the common mean effects. For example, like we can try to remove the pronunciation of the sentence itself from the movement of the combination of emotions and then the sentences. And then we will reach to this normalized curves. So we use them to do the inner product with all the additional effects in every groups. So for example, we use this curve to do the inner product with all the with this kernel to be fair for, and then to be angry, and then we can see like for the final scores, the fifth class, the angry will get the highest scores, and then we can further do some classifications based on the scores. So in summary, it can be achieved as a way to do the dimension reduction. So for example, we have this 17 action unit evolutions from the video, and then we can transform all this the curves related with times into just a simple matrix to do the further analysis. So this is like one way that we can utilize the information that we find from the latent patterns. So for the results, first, let me show you some results for the simulations. So the with the classical F-test of predictive value to be number 0.01, this is the ground truth of the simulated data that we generated. And then this is the results that we evaluated with the noise level to be 0.05. So it means that we add little noises on this data and then try to estimate back to find the kernels in green in each group. So we can see that with only a little bit like discrete points here, generally it works good. But however, with the noise level to be a little bit larger, you can see the shape is not kept with the classical f-test. And here I set the critical value to be 0.01, which is more strict, but if I make it a little bit larger to be 0.1, and then you can see the with looser constraints, it can capture more like the regions as we predefined before. Yeah, but however, like the shapes is still not that good when the noise level is large. So for the second method, the permutation test, as we said, like because removing the constraints of the normality assumption, we have more confidence to do the test. For example, this is the test result with 90% quantile. So when the noise is like small, the result, like this method obtained is similar to the previous one, although that the detected patterns are a little bit more smooth. Yeah. Most importantly, when the noise level is relatively large, with standard deviation to be 2, we can see that it still basically captured the shapes, although it also has some discrete points involved. But the main shapes are kept, I would say, like well compared with the previous method. And this is a comparison of these two methods in parallel. So if we define the kernel dissimilarity to be the distance of the estimated kernels and our predefined kernels, so we can see that the classical test method like goes up very fast. So like dissimilarity is something worse. So you can see how the permutation test behave. And then this is another measurement for the significant time zone matching rate. So we define it as how much percent like the same time, like the time zoom is detected correctly. So for example, you can see here with the permutation test, there is more than 60% of time zone is detected correctly, while the classical method, it dropped very fast when the standard deviation is large. So if we apply our method also on the Radice dataset, we can find like some different behaviors of the kernels. So for example, this is the disgusted emotion. And then for action unit 9 related with this nose vinculator, so you can see it is like going up. So when people is when people shows disgusted emotion, and then like they use more the muscles related with the nose. And then this is the test results based on the permutation statistics. Yeah, this is another, so here we can see that this muscle is locally strengthened under the performance of the discussed compared with the neutral case. And then this is another example related with the eyebrow. So it is like outer eyebrow riser. When kind of surprised, you also use this part of the muscle. So we can observe like two different situations. So this part, the muscle, the action unit is partially strengthened, while this is partially inhibited. So we can see like, although the time zone is detected both significantly under these two regions, well, it has different effects compared with the neutral case. And then this is the example related with the mouse. So we can see that when you feel disgust, like globally, the kernels is very high compared with the neutral case all along the videos. So we can see that this is very related with the disgust, also similar to the what they find in the literature before. So we can use this kind of pattern informations to study for the emotions and later to do the classification. So as a conclusion, so we first propose this combination of this ANOVA together with the F-tests in a more intuitive way for the limited sample size. So we use FANOVA to separate the common informations and then to dig out the additional group categorical influence. And then we use both the classical and permutation tests to identify the time zones, where the means of the different groups differ significantly. So we apply this method on both simulated data and then rev-dice data to evaluate the model's efficiency and then to extract out some emotional behaviors. And finally, for the patterns that we find, we can also call them normalized kernel functions of different groups. We can use them to do further classifications because they can partially reflect the remarkable main characteristics in grouped unities. So we have also worked something related with classification, and for the next step, we will try to pack up our knowledges and build the better model there. So thanks for your attention. And if any questions. Yeah.
Thanks for your presentation. So are there any questions or comments on the talk? No, I don't see any message in the chat or reactions. Okay, maybe I can comment shortly about the how useful, or you can comment why these kind of studies are useful for the company for which with which we are working. Maybe can you comment on this?
Yeah, so like I mentioned in the presentations, so it is a way that we can transfer the knowledge from the videos to the knowledge of computers. So for example, we can observe the information from the videos, but in this way, we can teach the computer, to teach the machine to know what is the patterns and then to make some guess for the videos by themselves. Also, like for this kind of pattern detections, we can, our human being can also find some like latent patterns, we probably know like by mind, but we cannot tell by words. So this is like some patterns or some common characteristics from the emotions. Yeah, and also this is like like the title said, it's a framework for the functional statistics to detect the group patterns. So not only we can use them on the facial videos, on the actual data, but we can also use them on the weather, for example, to detect the changing of the temperature or the changing of the rain quantities. Yeah, especially when we have a comparison or a template group together with a group that we want to study for some, for example, some abnormal cases, some extreme weather, something like that. Yeah.
Okay. Okay, so thank you. If there are no other comments or questions, I think we can stop for half an hour as planned. We have a break. And so we reconvene here at 11:45. Okay.
See you later.